Hello and welcome to the second day of International Science Week. This is one of our projects that's very dear to us. In this project, we group up two teams from different countries and they have to make a robot together. Today we have near us team TeaTime and Robotics. They build together the snake bot and we are very excited to know more about it.
So guys, could you tell us the main idea of the robot and the basics of it?
So the SnakeBot, can you hear me?
Yeah.
So
Yes.
the SnakeBot is a modular robot that is based off the shape of a snake, so biomimicry. And it's based off that so that it has a large range of movement. And this allows it to be extremely effective at going through small spaces and climbing obstacles and working in situations where humans aren't really able to operate well. And so we've taken this design and applied it to the idea of search and rescue for peace and development. And we're looking at saving people in lots of land search and rescue operations in rubble or in tough terrain as a reconnaissance drone that allows humans to gain the necessary information to set up a search and rescue.
Okay, and how did you get to the actual search and rescue idea? Like,
Uh,
yeah. Okay.
So we went through developing our context. You'd given us the original of peace and development, and we wanted to see what was around that. And what we found were fields like emergency services, communication, the military, security, the environment. And we found things that linked all of this were search and rescue, which was a big interest to us, as we thought a good way of benefiting peace and development with our robot would be tackling this issue. And so following this mind map, a simple brainstorm, it led us to be able to focus our sights a bit narrower on search and rescue.
Okay, and was this the actual first design of the robot, or did you get through more?
So we started with concept ideas, which Karen can tell you about.
So when we were designing this, we went through 4 different concept ideas. So one of those includes our final design of the snake bot. We also have a similar design, which is the spider bot, which also takes the form of another animal. This one was more designed towards caves and working in more uncomfortable terrains, and it would use the 8 legs like a spider to kind of walk on different terrains and still manage to get through it. You then had the land surveillance rover, which uses wheels and a drive base, which means that it's less likely to work on a uneven surface, and so it's more ideal for roads. And then you have a bracing and stability robot, which is designed for unsafe kind of areas where there could be falling buildings or collapsing buildings. And so its idea was to kind of stabilize the area and kind of build a room by expanding outwards and leaving a safe space for survivors.
The reason we chose to take the SnakeBot forward was because when looking at the different fields of search and rescue that we could benefit using our robot, we found that the SnakeBot was likely to be the most versatile and able to act in the most situations with the correct additions to it. And so what we did was research it further to allow us to better understand the design and make the adaptations that we wanted to make it a more effective design for search and rescue specifically. So what we found mainly from our research were 3 key problems with the SnakeBot, and that was the use of a tether cable, which meant the SnakeBot wasn't extremely viable in real life situations as of yet. And so we wanted to be able to remove this and make the SnakeBot remote, making it a true reconnaissance drone. Additionally, control was a huge problem faced by the people who initially developed this, which was the Carnegie Mellon University. And the reason control was difficult was because you can have a large number of modules which all have to move in sync for efficient movement. However, compiling all these controls to be effective is very difficult and takes lots of time to learn for the robot. The last main problem that we found were the mechanics. The original robot design was developed as a prototype and shown that it could be used in medical fields and search and rescue fields. However, in reality, the mechanics behind it weren't necessarily suited. The main fault in this was the housing, which was not resistant enough to compressive force or tensile strength that may be introduced to it in a search and rescue scenario, and the waterproofing of the joints. The joints are the key part which allow the extreme movement of the robot. However, also the weak points which make the robot vulnerable. And so we aim to strengthen these as much as possible. As a result, we developed a specification as seen on the right-hand side of the screen, and we developed them into primary, secondary, and other points that we thought would be extremely important for putting into our robot. We also considered the ethics, and being a piece in development robot, we thought this was extremely important. The SnakeBot as a robot design aims to look at search and rescue, but this causes a number of problems while also solving others. An example of a problem it could solve was where humans cannot enter hazardous situations. For example, the Fukushima Daiichi nuclear disaster in 2011 created extreme amounts of hazardous waste, which rendered the area unusable by humans, and they found it very difficult to remove nuclear waste from the area. However, if a SnakeBot had been invented at the time, the SnakeBot could have easily traversed the field and the narrow spaces where nuclear waste was caught and extracted it without much problem. And though attempts were made to use robots, the robots were too large using wheels or other forms of movement that were not really suited to the terrain, and shows why something like a SnakeBot will be more useful. However, we found there were three key problems regarding the ethics of the SnakeBot. The first one was priorities. Would it replace the jobs of current search and rescuers? How would it replace humans? And this is a problem that is extremely that is discussed widely in the media about robotics overall, and is a fundamental problem of looking at whether the robot should be able to choose who is saved. The second problem we found was looking at the hype behind robots, where companies usually sell their robots with lots of hype around what they are able to do and their abilities. However, with very little regulation to manage these claims, people can be led to believe robots are somewhat superheroes and can do all these tasks that they may not be able to do. The last problem we found was that it could be a double-edged sword. And in the same way that a SnakeBot could save lives, it could also take lives, being used as a weapon in the military. And this is something we wanted to avoid, as it greatly contrasts ethics. And so the main way we found of addressing all of these with the least ethical barriers in the way was using Asimov's laws of robotics, looking at whether a robot will be able to harm a human being or humanity, and whose control it will be under. The laws state that the robot should not indirectly or directly harm humanity, must be controlled by its owner, however still maintain its own existence.
So this is the final design of our SnakeBot. It's been designed so that it can partake in all land-based search and rescue missions, and it can aid humans or work on its own. So the main adaptations from the prototype version have been to improve the casing in order to make it waterproof and less susceptible to damage. So this would mean that it could go in areas where it might not be perfectly dry, and it could be easier for this robot to go in than another one where its electronics depend on certain conditions. We've also included camouflage coloring, as we're not sure what sort of search and rescue missions it might need to go on, and it might need to stay hidden, firstly from animals, and secondly from people who might not want our technology to be there. And then it also uses a range of different sensors in a pentagonal arrangement, and this would include a torch, ultrasonic, microphone, speaker, and gyroscope, which means that it'd be able to sense and know what it's doing and the location without having to have human interaction too much. And then it would also be able to have a adaptable amount of modules. So in the picture shown, it has 7 modules, whereas that would be able to be expanded and possibly shortened. And it also means that it'd be able to do this even if it's broken and snapped, it'd still be able to activate and work.
So a key development that this design has made on existing prototypes is the use of better modules, and there are both benefits and drawbacks to this. Of course, with a design like this, it can always be optimized as technology becomes more compact and more efficient, especially regarding sensors and batteries. We aim to put individual batteries in each module to allow the robot to be remote, and cover each of these modules in a titanium or carbon fiber casing, which has a high tensile strength and compressive strength. However, the main problems, as you can see in the CAD, is the limitations of the movement for these joints. For a more durable robot, we've had to sacrifice a small amount of maneuverability, meaning some of the gaits of the robot in terms of climbing and moving through very small spaces can be restricted. As technology grows, we can develop this with the use of smaller and more modules. However, at our current stage, this is what we have. And so now we'll go on to the code and how we're addressing some of the key issues we found with the original SnakeBot, particularly regarding control.
Yeah, so for our code, we decided to go with machine learning algorithms because that makes it so much easier to code the robot, because we don't have to individually make all the algorithms to let it control itself. We chose to use Q-table algorithms for our machine learning because it is much more effective at learning robots than, for example, a neural network, because a Q-learning algorithm doesn't need a simulation like a neural network does, because it's based on one agent systems, unlike a neural network that would use, for example, 100 to 200 different simulations of the same situation at once. The way a Q-table works is like you see on this table here. It has 2 axes. One of them is for each action. For example, the horizontal can be actions, and then the other lines are for different states. For example, what the position of each joint is, what the ultrasonic sensor sees, and stuff like that. So the specific thing you see on this picture here is what we call the exploration phase of a Q-table. In the start of it, it just tests out every different type of action for every different type of state, and then it gives it different amount of points after how well it does. In this situation, we would use the accelerometer to measure the speed in which the robot was going for, and the larger speed on the shortest time gives it the most points in this situation. After this exploration phase, it would move on to a refinement phase, where instead of doing all the different actions and seeing how it goes, it only works on the high point nodes. So, for example, in this situation, it would be around the center here where it's all 0.8, 0.9, and 1s. And then it would continue working on them, trying different combinations of them to see what works best. To do all this processing, we had to use a couple of sensors, mainly the accelerometer and gyroscope for measuring how fast is it moving, where is it in space, but also the encoders on all the motors on the joints, so that we actually can make kind of a digital map of how the robot is positioned, so we know how to move it. On top of that, we also had a sound sensor because we want to be able to listen in to where the person is. Because if not, there is no use in having a reconnaissance run if we can't do reconnaissance. So what we would do is make the sound be kind of a signal for where it wants to go, and then just continually run the code until it comes closer and closer to the sound until it finally found it. We also want manual control of it, and that would be done through FM radio communication because there's already so much technology in FM communication for control like this. And to do this, we would need different Q-tables for all the different directions. But we also need different Q tables for other reasons, because there's a big difference in moving around in an urban district as unlike, for example, a cave. So we would have to learn the robot different types of environments. So we would end up with a lot of Q tables. And what I would have liked to do if we had the resources to it is have a camera that would automatically recognize the kind of environment it is in and change over to the Q table that responds to that type of environment. For example, if it sees a bunch of houses, malls, and stuff like that, it would switch over to the urban one. But if it sees a bunch of wet, dark rocks, it would switch over to its cave Q table. Yeah, so that's basically the thinking I've done behind the code. We also would like to have like a microphone system on it, kind of like a walkie-talkie, so you could communicate with the other person.
Yeah. And so overall, that's our snakebot design, but there's a couple key advantages and disadvantages I'd quickly like to highlight. We've made huge adaptations and improvements upon the original designs to be the best suited we think it should be for search and rescue. However, this comes with limitations as just described. This requires a lot of preliminary control work to ensure that we can achieve a remote control, and also requires most likely expensive small battery modules and high quality materials to be suitable. This means it would be potentially difficult for research teams and national services to implement these robots easily. However, as technology develops, I'm sure there'll be ways around this. Thank you.
Whoa, that was great. Cecilia, that was really great. You really got the point of actually both the turns on the team. Like I think you're the first player that actually also included the team of peace in your robot.
Yeah, we thought it was really important because ethics are always what stops robotics progressing. And as we've seen in recent times, you've had these huge advancements by companies, but they constantly come under scrutiny from the media and religion and other, huge social outputs. And so it makes it very difficult to start implementing robotics into the future, which is what we want to do for sustainable development. And so it's really important to look at how we can appease to society to make this a viable robot that will actually help save lives in the end.
That really is great.
Yeah. I think a key ethical issue we did avoid with our design, we initially looked at making the robot being able to save people on its own, but we thought, and we realized very quickly that this would create a whole host of new problems. Especially regarding whether a robot should choose between two different people trapped in rubble. Who should it save? And so we decided that leaving that up to using a robot as only a reconnaissance drone would provide more than enough information for potentially two human parties to set out two different rescue teams and save both the people without the robot having to sacrifice one.
Yeah. Whoa. One more thing I want to ask you, and after that, I think we're done. Do you have fun?
Yeah, a lot actually. I think it was really interesting. I don't know a lot about code, but from Ronald, I was able to learn quite a bit about Q tables, which is something I don't know anything about before this. But I was able to learn about how it can be used to help a robot learn its own movement. Which, regarding robots in biomimicry, which are becoming increasingly popular, like fish robots, I'm sure you've heard of, or snakes or spiders, it's extremely important. It's an extremely important form of code to make them viable, and that's been really interesting to learn about.
Yeah, it was also really fun to have like one project to try to use that kind of knowledge on, because earlier I haven't really had a theoretical use for machine learning code. So I only had to do random practical tasks at the middle of the night when I had time. So having a project that I can actually sit down, read all the theory on, and try to focus on the theory itself, it was really fun.
Yeah, I agree. I think that it's quite interesting to also learn about things that I might not have heard of before. So the snakebot in general, I think, is a great kind of premise. to kind of work on, and that's something I could work on realistically in the future.
It provides a lot of interest going forward in the future, like especially wanting to move into the engineering field, looking at how like people are taking from the world around us, the animals who have been urban search and rescue. Looking at the snake was definitely an eye opener.
Okay, I'm really glad. Then. Okay, so I think that was it for the second day of the International Science Week. If you have any questions, please leave them in the chat of the video. We'll try to get Hell Robotics and TeaTime to answer them as soon as possible, and don't miss tomorrow's video because we'll also have some fun and also learn something new.
Thank you.